Welcome, everyone. Hoping we're moved into a good Thanksgiving or a happy Thanksgiving, or at least lots to eat Thanksgiving. I'm going to see my other daughter down in Beaumont, Texas, which is a very long drive from here, but I'm excited about that, and I hope you guys enjoy your Thanksgiving. I don't want to put a whole lot on you on this video. We're going to cover an awful lot, uh, but and there will be another video that I will upload to kind of reinforce what we're going through uh, on this initial video from me. Uh, a really good video talking about what happens after percent passing after we calculate that, and then I heard a couple of comments that the guy the TA fellow that did a good job of drawing the sieves and some things like that, but he kind of left us hanging on the distribute grain size distribution curve. So that's where we're going to start up. I got a call from one of you guys asking if you needed to buy some uh, what's called Similog graph paper. Uh, no, unless you want to. Uh, most of this uh, I'm not sure. I haven't looked that far ahead. I don't think we'll have a whole lot of this kind of plotting in the future, but I could be wrong. But if we do, we'll do it in the same way. We'll use what's existing. So we're going to take up a little bit where you left off with the Miss Cahill gal, and then that fellow that did the video. And I don't even remember what my video was about. But at any rate, we're continuing to move into AASHTO and Unified Soil Classification Systems. Uh, this right now is really kind of straddling both fences, what we're going to talk about today. But the first thing I want to do is, oh, by the way, uh, on the on the essay kinds of questions and things like that, I kind of said something to one of you guys that always most of you are doing real good work as far as that. For the most part, all of you are, but I want you to don't write down verbatim, even if it I don't know how much I can give on my end, but even if it takes you a little bit longer, I'd like for you to take these things you're reading and responding in a discussion, and certainly don't copy and paste, but take them and put them in your own words. Uh, I want you to continue to write, and I'm going to tell you something. When I was in college, one of the best things what I would do with my notes or what was I read in the book is I'd put those things in my own words, and that's a learning experience. You get your kinesis or whatever you call it when you're using your hands and not just your eyes and your brain, but you're taking what's written in that book and you're interpreting it to your understanding, and that's learning right there. So as much as possible, I want to see you do that. First thing we're going to do is we're going to talk about this graph here. It's a Similog graph, and by Similog, what it means is this bottom line here, right going right across here, is the horizontal axis and usually known as the x-axis. In this case, these physicist kinds of folks call it the abscissa. There's probably a reason for that, but it's the horizontal axis, and the horizontal axis is a log scale. You see these lines are different spaces, but they're different spaces starting large and getting smaller in cycles. Like right here, this is a cycle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what that does is most of these charts are based on a log 10 scale, or and that has to do with exponential powers of numbers, and I just don't want to go there. Uh, But that's why this takes that in consideration. Uh, so let's just take this one I haven't used over here, this spot right here, this first cycle, and I'm going to count. We're at 1,000ths right here. So this is going to be 2,000ths, 3,000ths, 4,000ths, 5,000ths, 6, 7, 8, 9, 10,000ths, and therefore we're at 100. Same thing, moving from right to left. We're at 1/100th at this point right here. So we're going to be 200s, 300s, 400s, 500s, 6, 7, 8, 9, 10. Now, 10 right here, we're a tenth, but you'll notice this little dotted line going up to here. That's because I wanted to capture the number 200 sieve. It wasn't on here, but the dotted line was. So this is 0.01, and then I get into 7.5 right in here somewhere. So basically in here close, I'm going to call it right there, is 0.075, and look down here, that's the number 200 sieve, 0.075 millimeters. Now we'll go through the table. Matter of fact, we can do it, we'll just go back and forth right now and see this 4% passing. There's a trigger right there. In the Unified Soil Classification in AASHTO, AASHTO is anything uh, smaller than 35% passing the number 200 sieve is a coarse grain. In the Unified, anything less than 50% passing, let me push this up, I got a one. Anything less than 50% passing the number 200 sieve is a coarse grain like gravel and sand. So you know what that does for us right away? That tells us that this is coarse grain material, and you see the general classification we've talked about before. It can rule out, like in the AASHTO chart, A6 all the way through A7-6. Let me throw you down here. So if we were just, this was a clean chart, we could take this thing and just go whoop, whoop, and all we got to deal with is from here over to here, because there's no fines in clay like silt and clay materials in this soil sample. So that's a trigger to let you know you don't, when you start going back here to classify using the AASHTO classification system, you don't have to worry about everything over here. I went a little bit far with that X. Moving on back to where we are, we've got that. We know we got a gravel and our sand, but we have a coarse grain material. So look back over here. We already found let's go back to our number 200 sieve and see where that dot is. Move all the way over. I don't know, right here. Move all the way over. That's 0% passing. Look here at the number 2. Well, it would be really about right there, because it's 0.4% passing. But that's where that plot should be, probably up a little bit higher here. But it's okay right there. You keep in mind that this is a copy of a copy of a copy. Unless you start with new graph paper, it's going to change every time you copy it. But this is good enough for us to train with, and honestly probably good enough for the lab. Because a lot of engineers take a look at this curve right here and look at it. It's covering everything from 3/4 all the way through the number 200 sieve. So it covers multiple particle size. So that's just by looking at this curve, an engineer can say, well, that's a well-graded soil, and that's fact. So, but we're going to go, you know, through it, do the nitty gritty on this thing. So we looked at the number 200. We saw that 4/10. We plotted it and on the log scale, and we also plotted it on the abscissa or the linear scale. That's the vertical scale. Notice the vertical scale is evenly divided all the way. So we've got that. Now let's look at the number 100 sieve here. Its opening is 0.15. And I'm sorry, it has its opening is, let me see if I messed that up. I had to change that around. Give me a second. We'll go right over to my other thing going on here. Make sure we do this somewhat right. So we're talking number 100 sieve, and it is 0.15, and it has it actually has a 2.5% passing in this in my I'm using what was in the book, so that's a mistake, but a little one. So the size the size is 0.15, the passing is 0.25. So if the size is 0.15 right here, and we have 25% passing, we should be up here coming across and down, which this plot would actually be. I'm thinking that book is off. I think it was 15 and 15 passing here, or 14. Anyway, this is not right. This is not right. This is also 15 passing. So that puts us at 10, 15 passing, and it puts us at, lost my point, 0.15. And that's still not what I like. 0.15, if we plot it here, that's going to be 5% passing. I'm not sure about that. I may have gotten hung up here. I hate to call the book wrong. That's usually not the case. Just a minute. Sorry, I'm all over the map with this thing. It's 0.4. I'm sorry. It's 2.5 passing is the actual number for the 100. So this is 2.5 passing, 2.5%. Well, that's just not a whole lot. So we're somewhere right in here where we thought we were. If you can see, this would be 0, this 1, 2.5 right in here somewhere. So we're good to go right through here. That's good. I don't have any doubts that we're okay. All right. Now we've got the number 100 taken care of. We got the number 200 to taken care of. Now let's look at the number 40 sieve, which is 0.425 millimeters with 13.9% passing. 0.425 is going to be, this is 0.1, 2, 3, 4, 2, 5 right here. So this is 0.425 millimeter. That's the opening. And it says that we have 13.7%. So that's 10, 11, 12, 13.7. So we're good there. Let's move on to the number 40 sieve, which is labeled up here. And it is, no, I'm sorry, it's 425. That's what we just did. And 13.7. Let's move on to the number 10 sieve. 2.0 opening, 46.3 passing. So here we're leaving the number 40 sieve, 425, at 13.7% passing. And we're going to the number 10 sieve, which is 2 millimeters. This to me is it's a little cheating, and I'm not sure what, but this would be one. No, this would be one. The dotted lines really are added in some cases by me, in some cases not. But this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I think we have just a minor glitch in our graph here. But we're going to stick with calling 2 here. 2, 3, 4, 5, 6, 7, 8, 9, 10. So that puts us at 10 here. It puts us at 2.0 size if we were counting this as a 2, 3, 4, 5, 6, 7, 8, 9, 10. Counting that as a 2. I'm not sure why, but we're going to. So that's plotted at 46.3. It's a little more than 45, so we're good there. Go down to the number 4 right here, and here it comes down through here. So the number 4 sieve is 4.75 and 76.7%. So 4.75. Let's see, 1, 2, 3, 4, a little bit further than that. But that's in the area for the particle size, 4.75. And if you go up to 76.7, it would put you about 75 here, 76 here. So we're in good shape here. The 3/8 inch sieve has a 9.5 opening and a 92.6% passing. So that the 9.5 opening would put us at, there's 9, right? They're cheating a little bit, but that's 9, 10, so 9.5 right here where the line's coming down, and let's write that in there. That's 9.5 millimeter. So that checks out. Now at 3/8, 9.5, 92.1% passing. Here's 90, and that's 1, 2, 92.1. That's good. That's really close. So we're checked out good there, 92.1%. And then finally we have the 3/4 inch sieve, which is a 19 millimeter opening, and it had 100%. Nothing was retained in that one. So let's look at the opening. Let's see if we can find it. There it is. Because when you go, notice here we were at a whole number, and here we're in 10, so this would be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So right here would be about 19. 10 is over here, so we're going to call that 19 because that makes it easier on us. And honestly, these things don't have to be exact. Having said that, they need to be not just thrown together, but a lot of this stuff is hand drawn across here by engineers because perfection is not what this is about. in this kind of classification. So we have got them all plotted. And as you can see, once again, this soil, just by looking at it, covers 1, 2, 3, 4, 5, 6, 7 different particle sizes, because so these particles are well distributed. Okay, I think that went okay. We've got covered the percent passing, the plotting of the percent passing as it relates to the sieve sizes, and we have the curve was already drawn, but we would draw the curve, and that's what it would look like, and that's a good looking curve from what I've seen. And we'll look at a bad looking curve as soon as I get through with this right here, because I want to jump on to the coefficient of uniformity and the coefficient of curvature. I remember talking about coefficients way back when we first got started. But here we go. And I wanted everything on this one page, because flipping back and forth, and again, you will go over the same kind of material in that video, not the same calculations, but uh, the same processes. The guys are really good at presenting it too. Uh, so it's about a 16-minute video. I want you to watch that. Even though it's Thanksgiving, we have to have a discussion, so that'll give you a deal to comment. I mean, we have to have this discussion each week, so that will give us something to grade you by, and you would take that. I'll put the directions in the tailgate for next week. Is It'll probably be just like, I need 3 responses. I want those responses to be in your words, uh, to the best you can, and because I really want you to understand this stuff. And then, like I say, 3 responses. And if you want some kind of order, I need like 1 thing you understood and 2 things you didn't understand, or you can have 1 thing you understood. I mean, or maybe you didn't understand 3 things. That's fine. Or you understood 2. I just need 3 responses. That's how my rubric is set up, and it's a good rubric. Again, the bigger part of your grade goes into how you communicate what you know, not how much you know. Uh, this is pretty advanced material here for what for given your guys' background. On that note, though, I have noticed that some of you guys have been exposed to this, been in labs. I think James brought that up. That's pretty cool, and then someone but here's the deal. One of you said that at where I worked, they usually send this to the lab. Well, they'll always send it to the lab. You probably won't say, "Hey, come here, Scotty, and classify this soil." They'll have someone come out with test equipment. They'll get a core sample. They'll take it to the lab. They'll run compaction tests on it. They'll run all of these kind of tests in the lab, and then come up with what's called a geotechnical report for the site where you're going to build. Okay, but let's do some uh, calculations that are going to tell us a little bit more about the soils, and those are the 2 things that we have touched on: the coefficient of uniformity and the coefficient of curvature. Uh, the coefficient of uniformity is right here. It's in your book, but this is the formula for it. And look at this. This is D60. So that is the diameter of the particle that passes 60%. Look at this 60 right here. So these are guesstimations from me, but pretty accurate. I went over till you hit the curve. I'm not paying attention to this anymore. I'm just, wherever I hit that curve, I'm going to go down, and this is a semi-dotted line till I get to 3. See that 2.5 and the 475? Well, that's a 3 when you count right there. So the D60, we did 60%. The D60 is 3.0 millimeters. Okay. Now look at the D10. This is D60 divided by D10. So we got to go to the D10, the diameter that is passing 10%. So that takes us right over here, go all the way over to the curve, drop down, and that's put us at a 0.03 right here. So go back over to the calculation and you'll see that that's 0.03. So now we have 3 divided by 0.3 because that's what this equal 3 and this equal 0.3. And if you divide that, you're going to come up with 10. That's the value of the coefficient of uniformity. Now, let's just go down, drop on down here to the coefficient of uniformity. And let's read this. Equal, when it equals 1, the grains are all the same size, and that means it's poorly graded. Now, what does ours equal? 10. No, look at this. If it's greater than 1, the grain size spans a large area, so it's well graded. We said that at the beginning, looking at how much we covered. So the coefficient of uniformity gives us well graded. Well graded. Now, if the coefficient of is 1, coefficient of uniformity is 1, that means the grain size is, I think I said that, grain size are all the same size, so it's poorly graded. If it's greater than 1, it's well graded, as ours is well graded. Now we had to calculate the coefficient of curvature. And so the formula is using these same passing rates. We have to calculate D30, and we found that it is 1 right here. And the way we did it, just to make sure we know, is we went over here to 30% passing, hit the curve, came down, and that told us that the particle size was 1. This is the particle size that is 30% passing. Doesn't matter what sieve, it's talking about the curve now, it's just passing, 30% passing. So we go to the 30%, go hit the curve, drop down, and it tells us that particles, all the particle sizes that are 1 millimeter, 30% of them pass. And so we put that down over here in this calculation. And we square it. You see that little number 2 up there? That means we square 1. Let's go over here, and D60, as you recall, is, wait, where did I get this one? D30 is 1 squared, that's right. D60 is 3 again. So over here in D10 is 0.3. So looking at this formula, 1 is squared, as that is the 30% passing size is 1 millimeter. D60, 60% passing, turns out to be 3 millimeters. And then the 10% passing, which would be right here all the way to the line, is 0.3. So that's 0.3. Now, let's carry our formula on to the next level. We got 1 squared equals 1, and we got 3 times 0.3 is 0.9. When you divide that, let me double check my math. Just hopefully we won't find something wrong at this stage, but let me look. 1 divided by 0.9 equals 1.1. So that's the coefficient of curvature right there. And this is the coefficient of uniformity that we arrived at. So let's go down to curvature. If the coefficient of curvature is between 1 and it's less than 3, greater than 1, it's between 1 and 3, it's a smooth curve, and that means it's well graded. So it's barely greater than 1, and I couldn't find a rule on there, but it's greater than 1, so that was well graded. Now, if the coefficient of curvature is less than 1 or greater than 3, so the coefficient of curvature is not less than 1 and it is not greater than 3. If it was either of those, it would be poorly graded, not smooth. Okay, folks, there you have it. I hope that was easier than it looked like for you to read. There's some reading that you might want to do. We will get back at it after Thanksgiving, but we still have things like, I wonder if I can change my camera without messing us all up. Let's give it a try since we're this far along. I want to show you one other thing. I think. I'm having trouble. There it is. Is that it? That's not going to do it. Sure would like to show you this. It's hallelujah. Here we go. I think we have it here. Believing that you can see this. So let me get back over here to operate. We'll get down to, that's what we just plotted right there. Now this is showing you some poorly graded things. This little curve, this curve right here is uniformly graded. So, but look, there's only 2 particle sizes considered, so that would be poorly graded. I hear they don't use the term gap graded anymore, but look at this one. It goes across, but from right in here through here, this is just a straight line. So they all passed at once, or they all didn't pass. So there's not a the distribution is all the same through here. And so that's a poorly graded soil. I don't know what they call that. But notice this one more time. It's covering grain sizes from here all the way over to here. So that's well graded. With that note, I'll quit with my tech toys before I mess something up. Hopefully, uh, this recorded and you can understand it. If you have a question that's bothering you, email me. Again, I want to try to keep it light over the holidays. Everyone, be careful. I'll have this posted up prior. This will be posted Monday. Thank you.